You're welcome.
Anyway, does anyone have the flash disk? Yeah, please ask something to the GT. Any questions?
What happened?
No file. Yeah, maybe because I gave my files on in the morning of the first day, so maybe my forget. Yeah, you have enough time to take it in Blackboard.
Yeah, or time is finishing.
Okay, let's work. Sorry for being late. Anyway, today I'd like to talk about something related to the Higgs boson scenario, which you have already listened several times, even during these workshops. And also, today I'd like to give you some unified interpretation for those kind of models, along with some specific direction. And also, I'd like to give you some new insight for the origin of the electric interface. So I'm Hiroyuki Ishida from KK, and I forgot to mention it. It's my great honor to be back here, because I was also here. And this talk is related to this work collaborated with Shinya Matsuzaki, who is now in China as a professor, and Raven, who is now in Estonia. Okay, let me start from the yeah, the place of light. Yeah, after finding of the Higgs boson in 2012, we are now trying to review the origin of the electrosignature breaking, namely the origin of mass. So thanks to the existence of the Higgs boson, we could write down this kind of potential, which is well known as a double potential. And until at some point, we are stabilized at the origin, but thanks to this negative mass term, the symmetry could be broken, and we are now sitting on some vacuum. And to realize the electric signature breaking, the important point is to have the negative mass parameter. But that mass parameter in the summer model is just a unique dimensional full parameter. Namely, that mass parameter must have some correction, radiative correction like this. But there's one argument started by Badin that this kind of quadratic divergence is not physical. Because we have relied on this argument in 1995 that shows that quadratic divergence itself can be subtracted by taking some boundary condition at the UV scale. And once you take that kind of boundary condition at the UV scale, you can simply neglect the quadratic divergence here. And the most important things for the correction is that physical scale, like this one.
This is just assumptions, not any principle can be.
Yeah, right. But it's
This
a
is
kind of boundary
it
condition.
says so, huh?
Yeah, it's a kind of boundary
You
condition.
should disregard such a nonsense.
Yeah, anyway, once you have been able to take that kind of boundary condition, since, as I showed you, since all the correction must be proportional to the mass itself, which is not shown here. Yeah, not shown here. Yeah, here. The RG running correction itself proportional to the mass itself. So once we have take the boundary condition at the UV scale to be 0, there is no RG correction on the mass parameter. This is one of the criteria. Yeah, I don't have to repeat it now. So that idea is nothing but the classical scale invariance. So once you have been able to take that kind of boundary condition at the UV scale, so we can simply neglect it. You can simply forget about this mass term. So there is no mass parameter in the Lagrangian. And as you know, once we only have this quadratic coupling, we would like to, we might be seeing along with the kind of flat potential because this quadratic coupling itself is small enough. So we are now focusing on this kind of direction, which are almost flat. And that is nothing but conformal direction. So the nature itself might be seen along with that kind of direction. But since we do not have any dimension for parameter, I mean the negative mass parameter, so the symmetry cannot be broken. So we have to rely on some new physics to break directly symmetry.
So how do you get the Higgs mass?
Sorry?
How do you get the Higgs mass?
How do I kill the Higgs mass?
How do you get the Higgs mass?
I will explain later. For sure, I will explain. And there might be some guide for the new physics, which is nothing but the electric vacuum stability. You might see this kind of figure before. The horizontal axis is the renormalization scale, and the vertical axis shows the running Higgs quadratic coupling. So due to the top contribution, the Higgs quadratic coupling goes to the negative at some point. So in that sense, electric vacuum might be unstable. And when we want to consider some new physics beyond the standard model, to choose the conformal direction which I explained in the previous slide might be helpful because it relies on the scale invariance. And for the new physics, to add one additional scalar will be helped to stabilize the electric vacuum because the contribution from the scalar to the running of the Higgs quadratic coupling is positive, so it can lift up the running of the Higgs coupling. There is some overlap there anyway. So the essential point is some mixing between the standard model Higgs and the extra Higgs is essential. Probably the battery is running now. Yeah. I think so. Yeah, and that scenario is called as a Higgs photon scenario. The Higgs particle, Higgs field itself connects between standard model sector and the hidden new sector. Well, let me introduce some several kinds of realization in the Higgs photon scalegenesis. One is the particle realization, which is nothing but Coleman-Weinberg mechanism. So the scale symmetry can be broken by the quantum effect, such as RG running. And another one is called non-perturbative realization, where the scale symmetry can be broken by the non-perturbative effect, such as the hypercolor QCD, which James explained previously. Right. Anyway, in both cases, we are now seeing along with the conformal direction, but which is nothing but thanks to the scale symmetry, namely the nearly the conformal direction. And of course, we have to break that kind of scale symmetry, which predicts the light diatom. Okay. Which mass is around order of 100 GeV. And thanks to the existence of that kind of light diatom, there are several predictions at the, for instance, colliders. Thanks to the existence of that kind of light diatom, we would have new resonance like this way. This dotted line just shows the diatom, which can mix with the Higgs. So in that sense, we would have resonance, the enhancement of the di-Higgs, dielectric gauge boson production, as well as di-Higgs production. And also, we would have the Higgs trilinear coupling to be enhanced, which was calculated like this way. I don't touch the detail. But here, we would like to claim.
Sorry, the H prime is the diatom?
Sorry?
The H prime, you have the bottom left.
No, this is nothing but the mass eigenstate of the Higgs. Okay, here, I'd like to show you two claims from us. The one is, no matter what kind of models you have, experimental signals are almost universal because by the existence of light diatom, unless you are seeing along with the conformal direction. This is just a universal interpretation of the Higgs boson scenarios with the conformal direction. And the question here is, what is the discriminator of the models? So, I mean, those kind of experimental signature cannot be the discriminator of the models. And our second claim is that the origin of the scale breaking cannot directly be the origin of mass. I mean, this scale symmetry cannot directly be the origin of the electric symmetry breaking. Namely, there is overlap again. To regard this mixing term as a Higgs mass term, you should have the negative this mixing coupling. Otherwise, electric symmetry cannot be broken. And another question here is what can be the original of the negative sign. Then, first, let's examine with the two-Higgs model. Okay, when you write up the two-Higgs model with scale invariance, you can write down the Higgs potential like this way. And by using this kind of simple notation, you can rewrite this potential like this way. And actually, there is SU2H1 times this, U2H1 times U2H2 global symmetry. And this last term is regarded as the SU2H breaking term, which can break the part of this U2H2. And also this second term corresponds to the U1 actual breaking term, and which can be regarded as soft Z2 breaking term. So once you have this kind of term, you can break the symmetry between H1 and H2. And again, this is the scale invariant realization potential. And here, we just consider, sorry, there is slightly different for notation, but C0, 1, 2 are real and positive. And we are now saying that the conformal direction, and since we would like to see the conformal direction, which can be achieved by choosing this kind of direction. When we perform the rotation of the axis, you can easily see the conformal direction. And it just means the direction for the electric symmetry breaking is just deformed. I will explain by using this kind of simple pattern. This is just, I just rewrite this potential by using its waves. Originally, we are just applying this kind of axis. But once you want to see, when you take this term to be 0, one of the axes must be deformed like this way, and around here, the electric symmetry must be broken. But the assumption to realize the electromagnetic breaking here are following. First, you have to assume that the maximal aspect breaking, which is nothing but the C0 over C2 to be 0. And also, you have to have soft enough U1 axial or Z2 breaking, which can be realized by C1 over C2 to be small enough. Namely, from this first requirement, you have to neglect this term. And since we are now considering that H2 must be much heavier than H1, we can integrate out the H2 by using equation of motion like this way. And when you plug in this relationship into the original one, you can get this potential. So, as you can see, this negative sign is automatically generalized after applying those kind of assumptions.
But then you're going to have C2, the sign, you fix it to be positive or can be.
We have just fixed all the coupling to be positive. Yeah, actually, I will explain the more detail in the following slides. Actually, this mechanism itself called as the bosonic system mechanism. So when you write down the mass matrix for these two Higgses, like this way, you can imagine this is nothing but the seesaw mass formula. And since this determinant is negative, one of the eigenvalues must be negative. And in case of a fermionic seesaw, this negative sign doesn't matter because we can use a chiral rotation to absorb that negative sign. But in case of a scalar, you cannot do it. So this negative sign must be physical. And we can reinterpret that this kind of deformation as this wave to be negative, which is nothing but the inert Higgs model. Yep. So in this sense, the bosonic seesaw mechanism also provides the same low energy signatures because we are now seeing along with the conformal direction, so we should have the light enough diatom, which can contribute to the dielectric production or the Higgs production or deviation of the triple Higgs coupling as well. So in that sense, again, those kind of collider signature cannot be the discriminator of the models. But that kind of bosonic seesaw can be realized by using hidden fermionic QCD. So the shape of the potential itself is almost the same, completely the same as the 2-Higgs model case because we just have the composite Higgs in addition to the elemental Higgs. And thanks to the thanks to the scale invariance, we do not have the Higgs mass term for H1. But thanks to the non-perturbative effect, we can have the mass term for the composite Higgs. And this parameter must be positive. And thanks to the Yukawa coupling between the hypercar fermion and standard model elemental Higgs, so we could have the mixing term between elemental Higgs and the composite Higgs. So here, you can imagine that that maximal mass spin breaking can be realized by the scale invariance. Since we originally do not have C0 term. And softly enough, U1 or Z2 breaking can be realized by the Yukawa coupling between hypercar fermion and elemental Higgs, which is nothing but this C1.
Okay, explain the soft enough meaning. Soft enough.
Just comparison between this C1 and C2.
Small
yeah,
enough.
C1 must be small enough compared to C2. This is just coming from the Yukawa coupling, and this is just coming from the non-perturbative effect. So this C2 must be greater than this C1. So both of the assumption in the 2-Higgs model can be naturally realized in this fermionic QCD case. Yeah, both of them are automatically incorporated in our model. So as I explained, the very origin of the negative coupling could be hidden QCD. So and also theoretic hidden QCD predicts the existence of the hyper QCD pions. So this pion can be the completely definite discriminant of the model. And also, as I explained, that one parameter is small enough so that this pion also light enough. So in our model, we can predict the existence of the light diatom as well as light enough hypercolor QCD pions. Okay, let me conclude. I have explained about the origin of mass, which can be realized the existence of the negative mass in which is assumed in the standard model. And this mass parameter would have some origin thanks to the existence of a Higgs photon extension. And also, we might be seeing along with the conformal direction. Thanks to the existence of the Higgs photon, the negative, in case of just Higgs photon extension, we need to assume the negative coupling between the additional scalar and Higgs boson. And since we are looking at the conformal direction, there must be light diatom due to the scale symmetry breaking. But this light diatom only gives you the universal signature wider, so this is nothing but some kind of universality class. So as I explained, by using the 2-Higgs model example, we have to assume, in case of the 2-Higgs model, that the maximum acid breaking and soft enough U1 or T2 breaking. But hidden ferromagnetic QCD dynamics could be the very origin of the negative Higgs mass, as I explained. And in case of our model, there is the not only the light diatom but also the pions. So this pion can be a discriminator. And near and or future collider experiment will deliver you some hint of the origin of masses, because we could see this kind of pion on the collider experiment. All right, that's all. Thank you very much.
Short question.
So here you use two Higgs mass example. Is it possible we just consider one scalar signal?
Yeah, for instance, that scalar is a kind of diatom. Of course, we could have the similar things. Yeah, actually, this is the summary of the universality class here. So along with the conformal direction, we would have several kinds of the models. But all the models can have the similar experimental signature, I mean the collider signature. Because apart from the light diatom, all the particles are heavy. So we cannot see anything. So, but you know, the light diatom can give you some experimental signature. But only this hidden ferromagnetic QCD have another signature from the pions. So once we will find that kind of signal, those kind of models must be killed, and our model could be survive.
What is the mass range of diatom and the couplings of diatom to the sum of particles?
The diatom mass is below TeV.
The TeV.
Yeah, several hundred GeV.
How about the couplings to the standard model particles?
It depends. It depends on mixing.
Depends on the mixing.
Yeah, it could be 0.1, but 10 to minus 2 or.
That can be easily detected.
Yeah.
In WW.
In other words, can be easily killed.
Oh yeah.
But why does dilaton light?
Yeah, because we are now looking at conformal direction, and breaking of the conformal direction is directly related to the electric symmetry breaking.
But at quantum level, there will be a trace anomaly.
Yeah, I'm sorry, we don't care about that kind of trace anomaly.
No, I don't think you will can ignore that.
But is that subtracted at the unit scale? Is that subtracted at the unit scale?
I don't think and your dilaton is not Higgs, right?
No.
So it's different.
Yep.
I mean, basically this dilatation current del mu d mu will be proportional to trace of energy momentum tensor, which involves the delta function of the your theory, everything. Standard model and hidden section, all of them will contribute to the T mu mu at quantum level. And some of them will have non-zero condensation, like a glow condensation or cubic condensation, etc. So all of them will contribute to this divergence of the dilatation current. So I don't think, I'm not sure if it's a good picture that you will have enough dilaton.
Let me take it back.
Yeah, maybe we can.
Yeah. So time's leaving, we should move to the next. So first we think okay, the next talk is